always available to go back and listen to. Today, we're just going to jump right in to our presenters and hear what they've been doing thus far with the simulated data sets. We're going to start off with the folks that have been working with multifan, and then we're going to go to a team working with stock synthesis. And then we're going to end, we'll have about 30 minutes or so to see how far we get along, but at least 30 minutes to have a discussion afterwards. And again, just a reminder, this is work that's in progress. And we really appreciate the presenters coming on to share how far they've gotten so far. And this is all kind of leading up to a workshop in March that's going to occur in New Zealand that we have been sending out information about, and we'll continue to do so as we move forward. But that's kind of the culmination of this this simulation experiment, is the workshop in March. So with that, without any further ado, just going to check with Simon that we, yes, I see the recording. Great. So we're doing that. All right, so to start off, our first presenter is Nicolas Ducharme-Barth. He is currently a stock assessment scientist with NOAA Fisheries, based at the Pacific Islands Fisheries Science Center in Honolulu, Hawaii. However, prior to that, he spent 3 years in New Caledonia at the Pacific Community, or SPC, where he had a real hands-on opportunity to learn about spatial models and multifan CL, or MFCL, as part of the team that developed tuna and billfish stock assessments for the Western and Central Pacific Fisheries Commission. So Nicolas is going to be presenting on behalf, or as part of team MFCL, and I'm going to just pass it over to you, Nicolas, to get started. Thanks for being here.
Great. Thank you for that introduction, Aaron. Let me share my screen. Okay. All right. Hopefully you can see that okay.
That looks perfect. Thank you.
Great. I'll go ahead and get started then with Team Multifan CL, Team MFCL, what we've done so far in this spatial stock assessment simulation experiment. But before, I'd like to thank the organizers for putting this together. I think we've had a lot of fun with this project, and we've learned a lot along the way. So yeah, really appreciate you giving us this opportunity to play with an interesting data set. So Team Multifan CL, there's actually a whole bunch of us, and I'd initially wanted to get a globe on the side, plotted out where we all are, but we actually can't all fit on one side of the globe. So I've got a nice picture of the SPC campus in Noumea, since at some point, everybody on this list, Claudio, Nick Davies, Jemry Day, myself, Paul Hamer, John Hampton, Arnie Magnuson, Tom Tiers, and Matt Vincent, we all work there or are currently working there. But before we get into some results, go into a little bit of the history of multifan CL for those that aren't familiar with it. It's an integrated statistical size-based age-structured and spatially structured model for fishery stock assessment. It's been around for quite some time. It integrates the original multifan model from 1990 that is used to estimate growth and proportions at age from length frequency data. Integrates that with the Fournier and Archibald statistical age structured model from 1982. It was actually first applied to South Pacific albacore tuna in 1998. And then it was further modified in 2001 to allow for spatial structure, movement, and the inclusion of tagging data. So at its core, multifan CL was developed to analyze spatially complex fisheries with little to no age data, but where length or size frequency data and tagging data were available. So thinking on how multifan specifically tackles the spatial problem, kind of split this up into 3 different components. There's the tagging component, where the tagging data is release conditioned. So there's a few things that you need for that. You need the length at release, which is a little bit different from some of the other platforms. We don't use the age with our tagging data. You need the region and the time of year, so the year and the month when those tags were released. It also tracks these populations of tagged fish by release group. So you have multiple tag populations going forward in the model calculations. There's a few different likelihoods that you can choose from. We've only looked at one of them in this study, the negative binomial, but there are some other options available that are in different phases of testing. There's a few things that you need to do when working with the tagging data. You need to define a mixing period, so a period at which the likelihood is desensitized to those tags, kind of a period in which the model is ignoring those tags before they're really having an impact on the estimates. It's kind of the period in which you would assume those tags are well mixed with the untagged population. You also need to define fishery reporting rates, because this is a release conditioned approach. In terms of movement, there are 2 movement coefficients, bidirectional, so one in each direction, estimated for each adjacent region in the model. However, the internal parameterization is such that it can allow movement between 2 non-adjacent regions within a single time step. So this parameterization actually cuts down on the number of parameters that is needed to be estimated, since you don't have to estimate every single pair of regions. You can also specify quarterly and age-specific movements, and these can be estimated within the model if there is sufficient information in the data to do so. In terms of recruitment, it assumes, the model assumes a single stock recruit relationship applied to all regions. So the spawning biomass in all regions is pooled together to determine the total recruitment, which then gets apportioned into each of the different regions. And that apportionment can be estimated within the model. There also allows for temporal variation in recruitment. Again, that can be estimated. And this temporal variation can be shared across regions, or you can estimate individual regional recruitment deviates. And if you do that, it quickly explodes the number of parameters that you're working with, because you have one for every time step in every region, or n-1 time steps in every region. In terms of usage, MultiFan-CL is used almost exclusively by the Pacific Community SPC to produce assessments for the Western and Central Pacific Fisheries Commission, WCPFC. These are assessments that are predominantly spatial in nature. Most include tagging data and estimate movement, and most do not directly incorporate age data, although some of the recent assessments, age data is becoming available, so slowly making its way into the models. Some of the recently assessed species and regional structures, there's the WCPO skipjack, which was assessed last year, or this year, wow, 8 regions. And then big eye and yellowfin tuna in 2020 had 9-region model. South Pacific albacore with 4 regions, and then Southwest Pacific striped marlin was a single region, and Southwest Pacific swordfish was a 2-region model. The user base of MultiFan is quite small. It's typically people that have worked at SPC at one point in time, but there's no reason other people can't use it. It is a good tool. So in terms of attacking this spatial simulation project, we started off with the single region. we started off with the single region model, took a look at the composition data likelihood. It's kind of a multi-fan specific thing, but how to look at the structure for the catches, whether it was a catch errors formulation that was typically been used for multi-fan CL or a catch conditioned approach, where those independent fishing mortality parameters aren't being estimated as parameters, they're being calculated internally. Also how to look at the fishery structure and selectivity groupings. And as this was kind of the stage where we started thinking about what the 4-region model might look like. We also looked at the input sample size at this stage as well, and the inclusion of the tagging data. And so that 4-region model, it uses a kind of a fleets as areas, 20 fleets single region model as the baseline. It has a look at, we took a look at the selectivity groupings at that stage as well, kind of in conjunction with the single region model, and then started to layer on some of those spatial components that I mentioned before, the movement, the recruitment processes, the tagging data, and the mixing period associated with the inclusion of that tagging data. The models, at every step in the model development, were checked for convergence, so looking for low gradients and positive definite Hessian solution. Some of the modifications or fixes that had to be done to multi-fan CL along the way. So the catch condition model was a big update to multi-fan CL in the last few years, and so in applying this feature to the simulated data sets, it allowed us to do some more in-depth testing and I guess make some small fixes to how to handle initial conditions based only on natural mortality, and also how dynamic depletion is calculated with the stock recruit curve adjustment. And it also incorporated a chronic tag shedding component, which wasn't previously a feature in multi-fan CL, but Nick Davies worked hard to add that in so that we could better model the tagging data from the simulation. So in terms of the initial model that we used in the single region, we didn't work with the 5x5 spatial data. So we took that single region, one area data set, and we began with 7 extraction fisheries. So 7 fisheries that are just there to remove catch from the population, and then 1 index fishery, which we associated the CPUE index, the standardized CPU index with. And each of these fisheries we had initially set up as, for the selectivities, an independent age-specific selectivity curve, and that was parameterized using a 3-node cubic spline. And the long line in the index fishery, as indicated in the OM, or assumed to be non-decreasing. We started off with a pseudo catch condition model. This was at a step in the MFCL development where we're still transitioning between the catch errors framework before, where our fishing mortalities at every time step was an estimated parameter, to the fully catch conditioned approach. So the simulation project was a nice way of testing the equivalence of those 2 methods within multi-fan CL. We also started off with the kind of the go-to length composition likelihood in multi-fan CL, which was a robust normal, and we used the data set that had an effective sample size or an input sample size of 5 for the length composition data set. We also had a quarterly fishery and recruitment time step. And so on the right, you see all the components of the model that we assumed at values that were specified in the OM documentation. So didn't estimate growth, we didn't estimate steepness, we didn't estimate natural mortality, maturity, was fixed at the values in the OM documentation. The initial conditions we set to be equal to the initial conditions at equilibrium based on natural mortality. We assumed the general selectivity shapes for the different fisheries based on the descriptions in the operating model. The penalty on the recruitments from the stock recruit curve we took from the OM documentation, and also the CPUE observation error. So one of the first things that I talked about in that pathway of development was looking at the length composition likelihood. And so initially we had used the robust normal. And so each panel is a different fishery. The blue line is the robust normal model, and the orange line is the Dirichlet multinomial model. And the sparseness of that ESS05 data set caused a number of problems for the robust normal. It wasn't able to handle that all that well. So we made the switch to the Dirichlet multinomial, and it substantially improved the fit to the length data. You can see an improvement there in the figures. Also improved the fit to the index, improved runtime and convergence. So that was something that we were happy to see. In that application of the Dirichlet multinomial, it is a self-scaling likelihood for the length composition data. So you estimate 2 scaling parameters per fishery group, and here we defined 1 group for each fishery. That being said, this approach is sensitive to how you choose to group fisheries, and also the maximum input sample size specified, although the idea there is to set a maximum sample size that's large enough that the effective sample sizes aren't coming up, the asymptotes isn't reaching it, which we did in this case. The next thing that we had to look at was the transition to a catch condition approach for the treatment of the catch data and the fishing mortalities. And so you have 2 models here, model 30 in blue, which is the catch condition model, and then the equivalent catch errors model in orange. And the later half of the time, or for most of the time series, spawning biomass in the solid line, very similar between the 2 approaches. There's a little bit of a discrepancy at the beginning, and that was when we were still trying to iron out the initial conditions, but that was resolved later on. The other lines that you see there is in the dotted lines is the spawning biomass when fishing mortality is 0. And so one of the metrics that is used a lot by SPC and within WCPFC for presenting stock status is this time dynamic depletion, which is just the ratio of the fish to the unfished. So when you take one over the other, you get this depletion time series, a dynamic depletion time series. And so just wanted to define that quickly because you'll see some depletion plots in the following slides. In terms of the fisheries grouping for the single region model, we looked at 3 different grouping types. Those are models 34, 35, and 37, where that first model, 34 in the blue, is that single region model with 7 extraction fisheries, 1 for each gear, and then the 1 index fishery, and then 7 selectivity groupings and length composition groupings. And so made the decision to group the index fishery with the long line fishery. Also looked at another formulation, kind of getting more towards Fleetz's areas with 16 extraction fisheries. So those are gear region specific. So that's when we still working within a single region framework, we use the data set provided with the 4 region structure. So had 4 index fisheries there. But again, we had just the same 7 selectivity and length composition groupings that were gear specific that we saw before. And then we also considered a model with, again, the same fishery structure, 16 fisheries that were gear and region specific with 4 index fisheries, but that when possible allowed for gear or region specific estimations of selectivities, although we still kept all the index fisheries grouped together for selectivity. And then we also kept the same 7 length composition groupings that were gear specific, again with the index fishery grouped together with the longline fishery. And that was for the Dirichlet multinomial, those length composition groupings. In terms of depletion, the different, I guess, fishery groupings in terms of selectivity and length composition, it didn't really make that big of a difference. Around the year 2000, you see some divergence from the 2 different approaches. Some slight differences in scale, but generally all following the same trend. Ultimately, we ended up with the simplest configuration of that model 34 with the 7 extraction fisheries that were gear specific. Yeah, we had a lot of discussion about this, and eventually, given the documentation of the operating model that indicated that selectivity was consistent across gears and space within a gear, we opted for this more simplified approach, and with the idea being that maybe once spatial processes are added into it, such as movement and the regional recruitment, that can maybe explain some of the differences that are seen. However, in an operational assessment, it might be treated a little bit differently. So the index fishery and an operational assessment would typically receive its own composition data weighted by the spatial CPUE, and the extraction fishery composition data would be reweighted by the spatial catch. And since we didn't work with that 5x5 more resolved spatial data, that wasn't an option for us in this instance. But yeah, I think there's an opportunity for further investigations into how fisheries are defined and groupings used to define selectivity and composition groupings. I guess if we were to start from scratch and use that more highly resolved 5x5 data, we might end up doing what's closer to what is done in the operational assessments, which is that second bullet. That being said, we went forward with the simpler Model 34, that blue line. So in terms of the current model, for the single region, we've got that 7 extraction fishery structure, 1 for each gear, the 1 index fishery with that index selectivity shared with the long line. 7 fisheries, 7 distinct age-specific selectivity curves using a 7-node cubic spline. There's a lot of 7s there. You had a long line and index fishery assumed to be parameterized with a logistic curve and not with a cubic spline. We went with the catch conditioned approach, Dirichlet multinomial self-scaling likelihood for the length composition data, and used, I think we'll need to check this to make sure it's consistent with the documentation of the data sets. But I believe we used that raw sample size for the length composition data. We didn't modify, well, what I mean to say is whatever was in the test data set, we didn't modify it. We didn't change the numbers of the length composition data. So whatever that was, that's what we used. And then in terms of the fishery and recruitment time steps, it was at a quarter. And so considered a number of models, some of which are very early on in development, so these blue ones here. Eventually we kind of narrowed it down to a clump of models that all had very minor tweaks between them. Ultimately ended up with this red line here, indicated by the two pink arrows at the start and the end. The biggest jumps, though, is when we updated the simulated data. I think back in March there was a data update, and that actually had a big effect on our estimates. And then we changed how we were treating the the composition data. We used, before we were modifying the sample size for each fishery observation to sum to 5, and then we switched to just using how it was provided from the simulation. So whatever the sum across bins was, we left it as is. And so playing with the composition data had the biggest effect up and down in terms of the results in those more recent models. So the other thing that we looked at for the single region model was the inclusion of tags. So mixing periods of, well, whether or not we wanted to include tags at all, and whether or not we wanted to include them with a mixing period of 4 or a mixing period of 5. And so a couple things happened when we threw tagging data into this single region model. So a model without tags is in blue, and then the models with tags but with different mixing periods are in these orangey reds. So the shape of the selectivity curve was sensitive to the inclusion of the tagging data in the single region model, but that didn't really translate to much difference in fits to the length composition data. The fits were pretty consistent, both at the aggregate and also at the looking at the fits to the mean length over time. Couple things I want to point out is here for the purse seine, this was something that we identified very early on. It looks like it's not fitting this early purse seine data all that well. There's a declining trend that the model estimates just not quite capturing as well as we wanted to see. So there could be some sort of process. There likely is some sort of process that we're not getting right with this formulation. And the other thing with this is the model kind of jumps up in around 2010 to match this purse seine data. And there's a lot in terms of the sample size. There's a lot of samples here, and so the model chases this a little bit. It fits it better than in the early period, but it chases this, and this has some implications when you look at the fit to the CPUE. So fit to the CPUE for the single region model, again, inclusion of the tagging data, not a huge effect. It's just in the last 10 years or so of the model period. Once the tagging data is in there, you start to see that blue line without the tagging data start to diverge from the orange yellows where tagging data is included. Going the wrong way. And then, as I pointed out before, the model follows that purse seine data up, all those high samples of purse seines, and it completely misses this bit of the CPU index. So that's a bit of a problem. That even though we identified it, given the formulation that we had up to this point, we still weren't able to resolve that. So a bit more work to do before we're completely happy with these fits. In terms of the fits to the tagging data, so the reason I show this slide is if within the mixing period, so models with tagging data, 4 was the smallest mixing period, 4, 5, and 6. Within a mixing period, so 1, 2, 3, 4, 4. the model is fitting the tags exactly because it's doing a numerical calculation. But when we change the mixing period, so we look at how the model with a mixing period of 4 performs that immediate time step after, it doesn't do so well. And so we had a big discussion when we were looking at these results. So mixing period of 5 and 6, the results were quite similar, but there's pretty bad misfit for this next observation for a mixing period of 4. So that was something that we wanted to account for and to bring through the rest of the development, is that the difference between those two models. Again, looking at the aggregate fits for each of the different mixing periods. So mixing period of 4, mixing period of 5, mixing period of 6. There's a pattern that emerges at these really high observations of tags. The model just, it's not getting there. So that's I guess an example of a persistent misfit or misspecification that we haven't been able to deal with at this point. Ideally, you'd like to fit these observations a little bit better. But maybe that will improve in the 4-region model. We'll see in a few slides whether or not that's the case. So in terms of the current single region model, we're left with a model in blue without tags. So this is the spawning biomass. And then the models with tags that scale the population down. Models 5 and 6, tag mixing of 5 and 6 are very similar to each other. The model with tag mixing of 4 is even lower. So lower mixing periods gives more influence to the tagging data in the model. So as you reduce that mixing period, you give more influence to the tags, and that's having the effect of bringing the model scale down. And those effects translate into depletion. So the model with the most effect of the tags, it's the lowest scale, it's the most depleted, the highest level of F. Overall pattern, though, in recruitments is very similar between all the different models. So something that I want to point out here is that at the beginning of the model period, there's very little information, limited length composition data. There's no CPUE data at this point from which to estimate recruitment. And currently in multifan, it's not possible to constrain these recruitments. I know in synthesis, you can have the early period and the main period of recruits, where that early period is constrained closer to 0 in terms of the deviates. And I think that's something that we would like to see, because this kind of jump in biomass is really spurious. It's the model is chasing very few composition data here, and it's not real. However, even though the model is going up and down in this period, the dynamic depletion for the same time period is very robust. So at least yeah, when we consider these different results, always have to remember to look at the multiple indicators of stock status, because one can definitely hide something from the other. So looking at the 4-region model development, again, we didn't work with the 5x5 spatial data. We began with that 16 extraction fishery and 4 index fishery model from the single region, and assigned those fisheries to the regions. And then we progressively added the estimation of quarterly movement. So we had independent movement for each quarter, and there were 5 adjacencies between the different boxes, the 4 different regions, and each had bidirectional movement, so that gave us 40 total parameters added into the model. Estimated the average regional recruitment distribution. It's an extra 4 parameters. And then the estimation of regional recruitment deviates. So 4 regions times n-1 quarterly time steps. That's where things really start to get out of hand in terms of the number of parameters, and you're adding 1,020 parameters at that stage. In terms of the tagging data, similar to the single region model, we're estimating or assuming a negative binomial distribution and estimating the overdispersion parameter. And we made all the same assumptions from the OM documentation as before, including the reporting rate, the assumed reporting rate for the different fisheries. So in terms of refining the structure, we considered a few different things with respect to movement. So movement in multi-fan-CL, you define a prior, a penalty on the likelihood where you either assume that movement rates are 0 or some value that you specify. And we considered a number of different, I guess, weights on those priors or initial values, I guess is a better word for it. And ultimately didn't make much of a difference in terms of the fits. Maybe slightly better fit with assuming kind of initial value of 0.1 for the movements. But as you can see, the estimated movement rates for the regions where there isn't much information, it's going to 0. So it's moving off of that initial value. We also looked at grouping of quarterly movements. So as mentioned before, you could have a quarterly movement estimated in each time step, or you could group the different time steps. So we considered a number of different groupings, and the one that had the best fit while also balancing parsimony. So we looked at AIC within nested models, and that was this two groupings of quarterly movements. So quarters 1 and 2 had the same movement pattern, and quarters 3 and 4 had another movement pattern. And just something to point out, which will make some more sense on a later slide, is the model is estimating, at least in the second half of the year, quarters 3 and 4, it's estimating a fair amount of movement from region 3 into region 1. And then we also looked at whether there was, I guess, information available to estimate age-specific movement. So we considered estimating age-specific movement as a linear function of age or a nonlinear function of age, so a logistic ramp in terms of the movement rates. So that's either adding 1 parameter for each movement coefficient or 2 parameters for each movement coefficient. And none of that added complexity was supported by increases in fits to the data. So we just left it at no age-specific movement. Something else that we had to play with was the recruitment. And I'm going to mention the orthogonal polynomial recruitment, even though we didn't ultimately end up using it. But as I mentioned earlier, when you estimate the regional recruitment deviates, that's a large number of parameters. 1,020 extra parameters. Not all of those parameters may be super well estimated. There could be regions and time steps where there just isn't a ton of information available. Particularly early on in the model period, we saw that there was that weird kind of hump of biomass initially. So one of the ways we tried to look at constraining that was to use this orthogonal polynomial recruitment, and it dramatically reduces the number of estimated parameters needed for regional recruitment. And it also had the effect of constraining some of those recruitments, particularly early in the model period, to be closer to the mean We didn't end up using the orthogonal polynomial parameterization just because there's a few things that need to be tweaked on it before it's ready for prime time. But at least in this example, it did show some promise, so it's worth mentioning here. We also looked into whether or not we needed to estimate those regional recruitment deviates. Again, that's a lot of parameters, and when we turn the estimation of that on and off, model selection criteria actually said that the degradation in fit did not outweigh the reduction in all those parameters. So AIC would have supported not estimating the regional recruitment deviates. And so kind of the biggest difference that you saw turning those regional recruitment deviates on or off is here illustrated in the region 2 CPUE, the fit to that. The orange line is with the regional recruitment deviates turned on, and it doesn't do a great job of fitting this early stuff, but it at least makes an attempt at it. Turning that off, it essentially just gives up, and it just fits smoothly through that first half of the CPUE period, and yeah, then it kind of it's an even worse fit. Let's just leave it at that. And the other thing that it did that was what we felt was unsatisfactory was in region 1, when you turned off those regional recruitment deviates, it put no recruits in region 1, which from kind of a biological standpoint, region 1 is kind of where you want all your recruitments to be, or at least that's what the OM is assuming. And so we didn't feel it realistic to, even though from a parsimony standpoint it was supported, we didn't feel it was realistic to not estimate those regional recruitment deviates. Another thing to point out is when we estimated the average recruitment distribution, the model chose to put most of the recruitments in region 3. And if you remember back a few slides, in the second half of the year, there's a lot of, well, not a lot, but there is some movement from region 3 into region 1. So while not biologically realistic or matching the OM, Multifan is finding a way to produce recruits somewhere else in the model to shove into region 1 where a lot of the fisheries action is happening. And there's a kind of a trade-off that you're seeing between the average recruitment distribution and the movement rates estimated between those regions. For the tagging data, that estimated over dispersion parameter went pretty much straight to 1. So more of a Poisson distribution than a negative binomial, it would seem. And then similar to the single region model, the model scale was sensitive to the mixing period that was assumed, although it really had a negligible impact on the fits to the CPUE index or the length composition data. It pretty much was just changing your scale in terms of the biomass, which had a trickle-down effect into what you assumed, what you saw depletion to be, dynamic depletion. So the current model, where we are with the 4-region approach, here we have the fit to the 4 different index fisheries, 1 in each region, and region 1, region 4, fits are okay. Region 2, not so good. Oh, wrong way. And it looks like in region 2, there's some sort of kind of cohort, year class type effect, where you just have these increases. Don't know if that's recruitment related or movement related. Either way, the model is not doing a good job of fitting that as it's currently formulated. So that's perhaps another bit of additional work that could be done to improve things. The other thing is similar to that single region model. When you have that increase in the composition data sample size for the Persane around 2010, the way this model is formulated right now, it's completely missing that, which is a bit undesirable. And I think the reverse actually of what we saw before. I'd have to go back to check, but either way, it's missing this. So something else to improve. In terms of comparing things between the 4-region model and the single region model, so the single region models, the solid line, the mixing period is denoted by the color, and the 4-region model is denoted by the dotted lines. We didn't run a 4-region model without tags at this stage. But the general trend is that if you look at the equivalent single region with the 4-region model, is that the scale is shifted up for the 4-region model, and that results in less of depletion. And I think I forgot to add the slide in of the regional specific estimates. But I'll quickly describe it. Is what's going on there is that a few of the regions show very high levels of depletion, and then there's a couple of the regions that I think regions 3 and 4 that are less depleted, and kind of act as a buffer to where the action is happening in the fishery, and that gives you the phenomenon of that 4-region model having a slightly better stock status than the single region model, where effort is not compartmentalized spatially. Another thing that we wanted to point out with the single region versus the 4-region model is moving to the 4-region model did improve the fit to the tagging data somewhat. It's chasing those high observations in one of the years a little bit better, and with the 4-region model, it's still not getting all of them. So there's something weird going on that the model's not quite able to match the dynamics. But there was an improvement, small improvement, when switching to the 4-region model. When we looked at the likelihoods between the two different models, it was actually interesting to see that the 4-region model had more conflict. So this gray line is the tagging data, and it doesn't appear to be in agreement with the overall minimum, is in conflict with the length data in orange, and you don't see that so much in the single region model, which was kind of interesting. You would have thought that if there was more conflict, it would be in the single region model than in the 4-region model. So that was a bit of an unexpected result. Now to move on to the replicates. As you see on the slide, we thought we were done, but something seems off. So for the single region model, the kind of the current final model for the single region is shown in the solid line. So the one without tags is higher than the ones with the 2 tags, with the tagging included. And the shaded region is the result of the 100 replicates fit with those different treatments of the tagging data. And I think in an ideal world, you'd like to have your solid lines inside of your shaded lines, but that's not the case. So we did a little bit of digging, and we didn't use the same composition data. Turns out if your treatment of composition data is different, you're going to get different results. So the test data set with that effective sample size of 5, that ESS_05X data is in the blue, and what we used for the replicates actually was the ESS underscore 00X, which is in the gray. And that much smoother length composition data, the Dirichlet multinomial, estimated a much higher effective sample size for that relative to that sparse data that we were initially fitting the models to, and it completely dominated the fit. So looking back here, you see that there is quite a bit of a difference between the models with the different treatment and tagging data. When we used those replicates that had the really good, the high sample sizes of that length composition data, the length comps just totally overwhelm the model, and you don't really see much difference between the different model runs that had the different treatment and tagging data. So we need to revisit this, at least correct it. But that is why you're not going to see replicate results for the single region or the 4-region model, because we thought we were finished, but turns out we did it wrong. So in terms of discussion, just kind of to wrap up quickly in a few slides. So some of the strengths that we discussed for MultiFan-CL, the tagging module, a lot of work over many years has gone into that. So we consider it to be an asset. The movement parameterization, that movement to non-adjacent regions within the same time step. And also the orthogonal polynomial recruitment parameterization. Even though not showing results from that, it definitely can greatly reduce the number of parameters that you estimate, and particularly if there are periods of your model that are data poor, it could be something useful to use, because when you go to the recruitment deviates parameterization, that's a lot of free parameters that can sometimes do weird things. In terms of a wish list to address some of the things that we saw in this simulation that maybe we weren't quite able to fit as well as we wanted to, but maybe would like to try to fit better if these were possible. Nick, if you're watching, I'm not saying to go ahead and develop this. This is just a hypothetical exercise. Time varying movement was one of the things that we discussed. The ability to estimate some movement parameters rather than either estimating all of them or estimating none of them. Related to that recruitment issue that we saw, being able to split up a recruitment estimation into an early period and a main period. So constraining those early period recruits when there's less information to be have a deviate closer to 0. And then also I think random effects in terms of estimating some of these different processes, so movement, recruitment, time-varying selectivity, rather than estimating them all as fixed effects. It could be better to treat them as random effects. And then in terms of a data wish list, so if the data were to be resimulated for a completely new experiment, perhaps finer scale composition data. 5 centimeter bins were a little bit coarse to see good modal progression, especially in those younger years where the fish are growing quickly. And then because we used the growth that was provided in the OM, we were able to get away with this. But for the data sets, the tagging data was provided the age at release rather than the length at release. And so we were able to convert or try to convert from age to length using the growth curve. But if we were to estimate growth internally to the model, this would be a bit problematic because then you could get a mismatch between the growth curve that you use to convert ages to lengths and the growth curve that is actually being used with the population dynamics estimated internally. So in terms of things that we would like to improve on this model, but don't necessarily know if we will get around to it, pending availability of of time for this project. There was a few systemic misfits to the length composition data, the CPE, and the tagging data that we'd like to, if we had the opportunity, to get another crack at it. So part of that would be we didn't use the 5x5 data in developing the model, and I think if we were to do things over again, we'd start with that 5x5 data and perhaps revisit the selectivity groupings and fishery structure as a result. It also looked like in some of the fits, particularly for that purse seine, the fit to the mean length data, there could be some seasonal or time varying component as the fishery is moving around within those big boxes that could offer some improvement in fit if a seasonal process or time varying selectivity was included. Also, another thing that could be good to do would be evaluating the tag releases relative to the regional boundaries. So a lot of the tags are released in model region 2, which is quite close to the boundaries with regions 1 and 3. So perhaps those boundaries are not placed in optimal places with respect to the tags and for the estimation of movement. Another thing that could be done is to define different mixing period lengths by release group. So if there are some that are closer to the boundary or further away, their level of mixing might be different. And then some other things that we need continued development of diagnostics for. We spent a lot of time trying to identify an appropriate mixing period, but the fits to the data were very similar, even across different mixing period assumptions, but the stock status was not. There were some large shifts, and so we really struggled with how to define an appropriate mixing period. Evaluating the fit to tagging data, it could be useful to have some better diagnostics for that, and also evaluating the estimated movement rates and what is informing that movement estimates. So an example diagnostic for that that could be developed would be like an empirical movement rate residual, where you look at what the movement rate indicated by just the empirical tag release and recapture locations and the model estimated movement, and seeing if those are consistent or if the model estimate movement is being pulled in a different direction due to the length composition data or the CPE index. And so lastly, thinking about some of those discussion questions that were posted in the presentation prep guide, limitations to implementing spatial stock assessments. We talked about model complexity being a potential limiting factor. At least in MFCL, the models are very slow to run when you add spatial complexity. The other thing that needs to be considered is that you actually have sufficient data to estimate all those additional spatial processes, particularly movement and recruitment. Another limitation to implementing spatial stock assessment could be the lack of tagging data to sufficiently estimate movement. In an ideal world, you wouldn't want your length composition data to drive your movement estimates, just because if your length composition is primarily fisheries dependent, you could have irregular spatial temporal sampling of that composition data. Also, you could have spatially varying growth. And if you've got either one of those or both of them going on, it could bias your estimates of movement if that's the primary driver of your movement rather than the tags. And so some general comments based on examples from the WCPFC is that in our limited investigation, non-spatial models tended to produce lower estimates of stock status that were more depleted relative to the corresponding spatial model, and that partitioning of fishing mortality and biomass in spatial models leads to buffering overall stock status, while some model areas show higher levels of depletion. And at least in the WCPFC, lack of regional specific reference points means that this behavior isn't always accounted for in management advice. And with that, it's the end of my presentation, and I should have done it at the top, but I would really like to thank all the other members of the MFCL team. This was a collaborative effort, and it was really fun working on this. Thanks.
Yes, thank you, Nicola. Thanks for your great presentation and very thorough explanation of all that you guys have done, which is quite a bit. We are at the top of the hour. We can pause here for a couple quick questions. Just noting that we'll have a full half hour after Rick's presentation. But if there's a burning question, yep, Rick, are you speaking? Oh, okay. And so if we have a question or two real quick for Nicola, we can do that now. You can either raise your hand use the raise hand feature, or type something in the chat. Just give a second here to see if anybody has something right away. I see Mark has a question. Go ahead, Mark.
Yeah, thanks, Nicola, for the presentation. I found it very interesting. One thing I noted is that you got no recruitment in one area, which was unusual, but you also have that in some of your actual applications as well. And I was wondering, is there anything inherent in MFCL that's being assumed that's causing something like that to happen?
That's a good question, Mark. And I'll take a stab at it. And if I notice there's quite a few of the team MFCL members in attendance tonight, if they want to jump in. I don't know about any assumptions, but Multifan has a lot of flexibility, especially when you're starting to estimate those regional recruitment deviates. And I think it's possible that in some situations, the same solution can be derived either by doing something with the regional recruitment deviates or with doing something with the movement rates. And so I think it could be an issue of confounding, especially if some of those regional recruitment deviates, because in the operational assessments, when you've got 8-9 regions and you quarterly time step back to 1952 or 1972, that begins to be quite a lot of parameters. So it could be kind of a trade-off between how the model chooses to fit the data, whether it does it through the recruitment deviates and the movement, a combination of the two. That's my intuition, but I'm happy for other people to correct me.
We'll say that we saw the same kind of confounding.
Okay, yeah, Dan Fu, go ahead, please.
Thanks, Nicola. That's a great presentation, very comprehensive work. Just quick question on the estimation of movement. The model seems to estimate, some of the model estimate quite high movement rates. Do you have a feel how much of that is driven by the tagging data and how much was influenced by the other data sets? I mean, you did a lot of sensitivities on the the mixing period. Do you have a feel that the mixing period causing has some influence on your estimate of movement rates as well? Because when you treat different mixing periods, a lot of those the tags has not been included in the model fitting, right? Should that have an impact on the movement estimates?
Yeah, that's a great question, Dan. Thank you. So if you look at this movement matrix for one of the example models, there's a lot of internal self movement, fish not leaving the region. There's not a ton of connectivity between all of the different regions, and suspect that's because there isn't, so the tags are only released in predominantly in one area. So you have information out of that area to get to some of the other regions, but you don't really have a lot of information to tell you what movement might be in the other direction or between these regions that don't have tagging, because it's so concentrated and not kind of spread out across the spatial domain. So that might be one of the reasons why we're seeing kind of this limited transfer of biomass between regions. And something that we were actually discussing today is what actually is driving these estimates of movement, whether it's the tagging data, whether it's the length composition data, whether it's the CPUE. And that was one of the things that we had on our wish list is kind of a better diagnostic of that, because we tried to do some profiles which maybe indicated that length composition was important, but we didn't have consensus within our group that was the correct conclusion. So kind of at least in this model, it's tough to tell, and we didn't have a great diagnostic developed today to really to tease that out. I see John's got his hand up. I'm sure he will do a good job of following up my answer.
Yeah, please go ahead, John.
Yeah, I was actually going to comment on another aspect. I think you covered that one pretty well, Nicola. The aspect I was going to mention was this Dirichlet multinomial size likelihood that we're still kind of learning about, but we were reasonably encouraged with what we found using it on the simulated data. You know, even though we had observed sample sizes in some of these data sets, you know, massive observed sample sizes. I think for the purslane fishery, is it fishery 6, that there were some, you know, quarterly sample sizes of over a million fish, that the Dirichlet multinomial was still down weighting that size data, you know, quite massively into single figures. So we weren't telling it to do that. That's what it was coming up with through the statistics of the Dirichlet multinomial. And inadvertently, we just discovered this afternoon that we were using different types of size data in the replicates, which Nicola alluded to. But these size data in the replicates, and we're still trying to get to the bottom of it. But the sample sizes, the observed sample sizes were very large, but the data looked much smoother and more regular, and the Dirichlet multinomial was coming up with effective sample sizes a couple of orders of magnitude above what we had used in the reference model data sets. And if you looked at the fits to the data, you could understand, you can see why that happened. So it was actually, if inadvertent, it was a good test to see how that those Dirichlet multinomial statistics respond to what it perceives as the quality of the data.
I might comment on that point that with such coarse length composition data, and especially for the purslane, not very many bins of that length composition, even having any fish at all, it's not surprising that the effective sample sizes go down to a very low number, because there's just not that much detail there for it to be able to capture.
Okay, well, I'm sure others have some more questions. I'll let you write those down and think about those, and we can come back to those lingering questions at the end in our discussion time. For now, I'd like to move on to Rick Methot, who's going to give us a presentation on what him and his team has been doing with stock synthesis. And as in way of an introduction, Rick is NOAA's senior scientist for fish stock assessments. In this role, he serves on the NOAA Fisheries Science Board and the NOAA modeling team, where he aligns fish assessment modeling practices with weather, ocean, and ecosystem modeling. He is active on the steering committee for CAPM, the Center for the Advancement of Population Assessment Methodology, and with work on developing standards for science-based fisheries management reference points. He has devoted much of his career to development of the stock synthesis assessment model, which is one of the models being used in the spatial modeling project, and one of the ones that he's going to be, well, the one that he's going to be talking about today. Rick, please go ahead. Thank you.
Very good, and thanks for that introduction, and thanks for the project. I mean, it's great for us to be working together on something like this, so I applaud the efforts and the challenges to be able to do the work involved to produce these data sets and for all the teams to work on setting up. So let me go ahead and start up a presentation, which will be shorter than one we had. From Nicholas's presentation, it's clear that their team was able to put a good bit of energy into this, and I think we probably don't have quite as much, but we do have some good information to share. Got it here. Okay, going to be talking about the SS3 models for this yellowfin case study. The team has 5 of us working on it, and you know, most of the work was done by Dan and Urgasan. Max has made a good contribution, and Catherine and I, you know, helped organize things a bit, but you know, they get a lot of credit for the work that we've been able to do here today.
Rick, we see it's not in presentation mode. If you
Okay,
could get
let
it
me
there,
work
it might
on
be a
that.
little bigger then, yeah.
Yeah, let me work on that. Hold on just a second.
The multi-monitor shuffle.
Yeah, no, I'm almost there. Did that work?
We still see the one with the sidebar of the slide, so
All
not in
right.
full presentation.
Huh. Better?
No. So, sometimes I think you got to stop sharing and then start resharing for those effects
That makes
to
sense.
come up. Let's try that. And if not, maybe we can zoom in a touch and we'll be okay.
No, I could get there. I have a couple minutes. Stop sharing. First, we need to stop the slideshow. Didn't have things previewed here for Microsoft Meet. Almost there. That should work, right?
Yeah, yes, that looks great. Thanks, Rick. Go ahead.
Good. Try this again. So just going over briefly the basic capabilities of SS3 with regard to the specific characteristics of this exercise. SS3 has a lot of the same characteristics as multifan CL in this regard, but let me go over what we are using here. The areas are basically virtual compartments. They're just units that have fish in them, and fish can move from one area to another versus a transfer coefficient. So you could have any combination of area movements, and each one is defined individually. They aren't defined as pairs. They're defined as movement from area A to area B without anything implied about movement from area B to A. They're all separate movement pairs. There's a global spawner recruitment pool that is summed across all the areas, and then recruits are partitioned out to the areas. So there's recruitment partitioning that happens, and that recruitment partitioning can be time varying. We are not invoking that degree of detail given the data that we have. The movement is as a percent transfer among designated source sink areas. And this can be a age-specific movement with some defined shape of that movement rates for, so young fish can have a different movement rate than old fish, according to some a kink in that curve. Importantly, fleets are assigned to a single area. So if you know what the catch of a fleet, you know the catch has come from a particular area. You can share characteristics among fleets such that you could have a long line fleet in area 1 and a long line fleet in area 2 that are different fleets, but you could have them share the same selectivity or catchabilities as needed. Tags are seeded into an area at some designated age, not length. We've not tracked the growth characteristics of tags, although it is an idea we are interested in implementing in SS at some point. So tags are come in as a designated age. And if you happen to have a tag group that spans a wide size range, well, you could break it up into small fish and old fish and create different tag groups out of it. Recaptured tags are then tracked over time to inform mortality, and the distribution of recaptured tags across fleets, which again represent only areas, will inform movement. So those are the basic characteristics, and clearly, very much similar because we're dealing with the same kind of problems as the characteristics you see in multifamily. In this particular model, we're working with 16 fishing fleets. Only one of these fleets, the longline fleet, is treated as having asymptotic selectivity with a logistic function. All the others are treated with a double normal selectivity function. We see some spikiness in these distributions, even when aggregated. And this is one of the characteristics that I'll get to later on. I have some concerns in that regard and how it's influenced our ability to have well-performing models. And in particular, this longline fleet across the 4 areas is something that is treated as an asymptotic selectivity and hence has the most influence. This size comp has a particularly large influence on inference about what the mortality rates have been in these fisheries. The catch in this model across these 4 areas, I thought I had a label in here. Nope. So area 1 in the upper left has by far most of the catch, and most of it is from purse seine. So we have a large catch of young fish in that area, 74% of the total catch. Area 2 has purse seine and troll catch. Area 3 just has a very small amount of catch, and it's all long line. And then area 4, again, has mostly troll catch, and then a smattering of other fleets operating in area 4. We questioned on what is the merit of even including area 3. We could have pooled area 3 with area 4 with really no loss of information about what we can infer for the data that are available here. For the tags, there is a large number of releases, but they're almost all in area 1. And we have 10% of those tags recovered, a little over 10%, but they're mostly by Persane, again, still in area 1, and very few are Persane in area 2 and Persane 4. So, we really have not very much direct information, very much sparse empirical information about movements between areas. But we do have a large number, especially in area 1 and 2, from which we should be able to infer the mortality rates of that area, except it's going to be confounded by movement to other areas, but we don't have any enough tags coming from the other areas to constrain it very well. And we also see that, in terms of the recoveries here, a very large fraction of the recoveries. Let's see, maybe Dan will have to help me on this one. The two sides of this curve must be the tags from area 2 are recovered mostly in area 2. That's what it's showing on the right-hand side here. In terms of our model structure, we also tackled this with a 1-area model and the 4-area model. In the 1-area model, it's treated simply as one pooled area, where we have a single abundance index from the long line and 7 fishery groups without having things broken up across areas. In the 4-area model, several of the fisheries get broken up across the areas, and we now have regional recruitment, and then with limited movement between the areas. We are not even allowing movement to occur between all the area pairs. Just looking at the characteristics of the situation, it's clear that the Persane fisheries operate in areas 1 and 2 because that's where the young fish must be. The fisheries are able to find it, and so that's where we assign most of the recruits as the base recruitment, and then it'll let some fraction of recruits occur in other areas. In terms of the time steps, the temporal sequencing of the model, we do it as continuous quarters. And so each quarter is effectively inside the model operating as if it's a year of only 3 months. And so that's the age of the animals are now reported in quarters. And so we have now put 28 quarters as the duration of a generation in the model. We did some work with Fleets' area, but principally we're just looking at the 1-area model and the 4-area model to date. We took from the description of the data sets and the simulation, we're using a Beverton-Holt stock recruit relationship with a steepness of 0.8, sigma R of 0.6. And then there's the regional recruitment apportionment. We have assigned movement rates between areas 1 and 2 in both directions, areas 1 and 4, and 3 and 4. So we are not allowing animals to be moving from area 2 to area 3 or 4. Again, we saw no tags going in that direction, and so we did not even attempt to estimate movement parameters for that configuration. Taking the growth, maturity, and natural mortality rate as provided. We're using a shared catchability for the CPUE. And now on the length comps, what we have ended up with, and I think this is something that may be worth revisiting, we did not use the Dirichlet multinomial. We did use the assigned sample size of 5 fish for every single composition observation. We did not use the total number of fish in the length comp as a sample. We just used the 5. And unfortunately, I think that has caused us to greatly underweight the purseine and some of the other large catches. And on the other hand, it's clear from just looking at the size comps, especially for like the longline fishery, even though it's a substantial fishery, the length comps were very spiky. And they were almost as if the sample itself for that quarter, for that fleet, only had less than 10 fish in it. So very spiky, and hence, I'm sure, quite masking of any of the recruitment signal that had been there. So I think, you know, if we are able to continue working on this, that we might relook at the sample size weighting for the length comp observations and to use the Dirichlet multinomial that is certainly available and functional in stock synthesis. Going to sort of our bottom line of what we see overall, you know, we were able to fit the observations pretty well. There's no really glaring patterns that are of lack of fit. The spatial model seems to do a bit better job with the regional difference than the single area model, which isn't surprising given how different the trends look between the 4 areas. Putting prior constraints on the regional biomass distribution in the spatial model, by doing that, by using the shared catchability, that helped a lot in getting a sense of the distribution of biomass. The data don't really seem very informative on regional recruitment and migration. And again, it's likely that these are confounded because there's just not enough of the right kind of information to estimate these parameters, because they are inherently confounded, and you need to have some separate information which can come from the tags in order to estimate it. And the very spiky length compositions for Sona fleets also probably contributed to this situation as well. What we find is that we ended up with comparable spawning stock biomass estimates between the 4 area model and the single model, but when we include the tagging data in it, we see some greater difference there. So better understanding of just what is causing that would be helpful. We find differences in estimation of the scaling parameter between the 2 models. And we see similar biomass distributions on areas. And we've had some difficulty, you know, sorting out the temporal structure. We tried doing this as a season within year model versus a quarter as year. We're generally happier at this point with the quarter as year approach, but we did do some investigation of the year season approach as well, which would have a different recruitment structure to it. So one of the questions we have, and here we're showing the CPUE trend across the 4 areas. And again, we see that in area 3, there is a very flat trend there, where there is very little catch in that area, very little trend in that area. And we also see that the seasonality, it seems to be some there, but we really, without the movement parameters into area 3, we did not attempt to try to reconcile what might be going on, in that there does seem to be some seasonality in the patterns in area 3, but we weren't able to take that very far. We do question whether or not we even needed to treat this as a seasonally structured model, given the patterns that we saw in the other areas. In the one area model, we looked at how long the time series should go back and what the influence of tag data should be. And in the 4-area model, we tried looking at the regional recruitment distribution over time and whether or not we could make it time varying, and tried to sleuth out just what it was driving the distribution of biomass between the areas, given that we don't have a lot of information. A lot of it's going to be dependent upon things like the assumptions about catchability across areas. So we have a number of area configurations that we developed here. And the main model we ended up with is the IO model in red, the single area model, 7 fleets, 1 CPU index, and then the 4-area spatial model. And I will have to turn it over to Dan if we're going to try to look into any of the details of these when we get into discussion later on. So when we do the 1-area versus the 4-area model, we see a difference in the upper left panel here of the scaling of spawning biomass. See very similar trends between the two, but we see that the overall model, single area model, shows a greater proportional decline than the 4-area model. And this is probably because of the 4-area model is better able to allow the higher biomass retention in areas 3 and 4, where we don't see the downtrend caused by the purse seine fishery in area 1 and 2. If we were to do this without the tagging data, which is, again, allows some degree of movement between areas, we see a closer agreement between the two. And that's in the lower right-hand corner here. The IO model with no tag and the IO4 model with no tag end up being pretty similar. And exactly what drives that difference, I think we would have to look at that a bit further. But it clearly also shows that the tag data are influential in driving the overall result to a higher level. As the multifan team, I think we would look further into the effect of the mixing period and whether or not that influenced the overall sense of mortality that we're getting out of the tag data. We did some degree of R0 profiling, and in the 1-area model on the left-hand side, we see that the model tends to fit better at towards the higher biomass trends, but it's pretty flat in the that area as well. And there was it's the tag data that is tending to push things to the right, whereas the length data and the recruitment trend. Now we asked, why is it that we end up with such a large recruitment penalty showing up here in the R0 profile? And I think this is because of the fixed steepness value. So that if you have a fixed steepness and you also certainly have a fixed catch in the model, so by profiling on R0, you're essentially profiling on the depletion early in the time series, and that causes a different trend in recruitment over time, but you have a fixed steepness. So I think what's happening is that as you profile to a lower R0, you end up creating a trend in the recruitment deviations that causes this penalty to show up here. I think if we had estimated steepness, you would not see such a high response in the recruitment deviations. Now, over on the right-hand side, we also see that the tag data are tending to pull the model towards higher biomass levels, as is the index data. And in this case, the fit to the length data goes in both directions. It degrades in both directions. So this model, the 4-area model, seems to be strongly constrained by the length data, and you know, that's makes some sense given how different the regions are in the length data that we have. Did some investigation of how far back to go with the recruitment deviations. Again, exploratory model runs. You know, we don't have high quality information back there. And so I don't think we need to put too much weight on this, but it is good to see that by going back further with recruitment deviations, we have pretty negligible influence on the fit to the index later in the time series. But we also see, you know, quite a bad bobble in the fit to the index here in the about 2005 to 2009. You know, that time period, there's a large sequence of deviations there that clearly came from somewhere and that we have not modeled. We did an age structure production model comparison. Essentially just fixes the recruitment deviations to 0, and we don't use the length data at all. So basically, we're just driving the model with the CPU and catch as if it's a production model. And in this case, the scaling is pretty similar. So you know what we're seeing in the analysis. Let's see, Dan, maybe you can put in the chat how we dealt with the tag data. I presume the tag data also is not in this one, but let us know if it was. In the 4-area model, we do overall quite well in estimating the fit to the index in the 4 areas. I think just as we saw with the multifan model in region 2, this area right here, I don't know if you can see my, oops, sorry. Don't know if you could see my cursor, but in the about 2006 to 2009, there's a large sequence of positive deviations in the fit to the index in area 2. And then we saw the same thing in multifan model. Whereas area 1, we see that the model is picking up that positive sequence of the index there in that region. So it would be interesting to take a look and work closely at what might be going on in that area.
Rick, I just wanted to let you know that Dan says in the chat that the tag data are included in the age structure production model. And that we can see your cursor as long as just kind of, as long as it doesn't say stagnant, we can see it.
Great. So I'll try not to keep bouncing it around quite as much. And then the fits to region 3 and region 4 are all quite reasonable here. In terms of the fit to the length frequencies, most of them are reasonable, and the handline in area 1 is not fitting the right hand shoulder very well. It's much more spiked towards the younger animals. Perhaps using a selectivity function that's more flexible than double normal could have been useful there. See, this is hand line 1. Let's go over to, so that one was treated as being asymptotic. And so that may have been, you know, not the best choice for that fishery. But overall, the selectivity curves and the patterns that we see in the fits are about as expected, given that we were working with a sample size of 5 for all of the composition observations. in some cases, here we're looking at the trend over time for each fleet of the mean length. In some cases, like PS1, let's go to that one down here. There's some pattern in the deviations here in PS1, and there's at least one of the others that it was not as close as I would expect it to be. But again, we're dealing with a pretty small sample size, and so the recruitment penalty and the tag data are going to be pretty influential here, potentially more influential than a sample size of 5. So perhaps this degree of difference is not unexpected. In terms of the RZO profile by fleet for the comp data, we not unexpectedly have a bit of a mixed bag in that regard. In all of this sort of work, the closer you look, the more patterns you can see, correct? And so in this case, that's the case. There are some fleets, and I think it's interesting here, and it's exactly as expect that for handline 1, we get a better fit at a higher R0, a pretty strong trend here. And I think that's consistent with what we saw on the pattern in the fit to the length comps. So that the pattern in the fit to the length comps wanted there to be more large fish, and that would be something that would occur if we were running the model at a higher R0. So consistency there in how the model is performing. But overall across fleets, some fitting a bit better at high, some a bit better at low. For the 4-area model here, things seemed reasonable, except again for handline 1, we see that this again is looking at mean length residuals. And here for handline 1, it's pretty much all negative residuals. And so that's, I think, an indication that the selectivity for that fleet is not quite dialed in at the right degree of flexibility. In terms of some of the fits to the tag data, we ran with a mixing period of 4 periods, and yeah, we were looking at the effect of only using tag groups that had sufficient recoveries after the end of the time period, after the end of the mixing period. Because in many cases, the number of the tags were returned within the mixing period. But we did work with a mixing period of 4, and with this change, we did not see much change in the behavior here. Many of these cases, we see pretty good fits to the patterns. Looking here in 2004, 2005, we see that the time sequence of tag recaptures is pretty much matched between the model and the data. Although there are other circumstances here in 2003 where there's more noticeable residuals, and some circumstances where it goes the other direction. So there's more noise in the production of the tag data than we understand. There must be some other factors going on that can allow such large number of tags to sometimes show a pattern like this, and sometimes show a pattern like this. And that kind of inherent tag group specific flexibility is not something that we have in the model formulation. I suppose if we, played with the initial mortality we might be able to do something with that, but we did not attempt it. In the, don't know what to say about this one. We do end up seeing some pattern at the end of the time series and recruitment deviations. I think we saw that with the multi-fan result as well. Again, with such large fisheries capturing young fish at the end of the time series, not surprised to see this kind of sensitivity showing up here. But we do see some fairly marked trends in the recruitment deviations in the 4-area model. And so it is interacting, I'm sure, with the the catches at the end of the time series. And this is also the time period where we have the tag recur. We don't have tags early in the model. We have tags late in the model. So the later recruitment deviations and the mortality of those recruitment events is probably interacting here at the end of the time series to be affecting the recruitment deviations in these ways. In terms of the biomass distribution, IO1 model on the, no, sorry, this is the all with the IO4 model. And with movement on one side and no movement on the, I'm sorry, no movement in this model configuration here. And we see the biomass time series, we see the steepest decline in biomass in region 1, which is where most of the catch has been. And we see the lowest and flattest biomass trajectory in area 4, which has the least catch. So no surprises there. But the absolute scaling of area 3 and 4 relative to the others is going to be driven strongly by the CPU-EQ constraints. And then the proportion of recruitments, we end up with most recruits at area 2 and smaller numbers in area 3 and 4. But it seems likely that this has been confounded with the movement and how little information we have on movement between those areas. But nevertheless, in terms of proportion of recruits to areas 3 and 4, it seems consistent with the overall model. Oh yes, and sorry, not doing enough clicks ahead of time. In the IO4 model, if we don't have movement, that's down here in the lower right-hand corner. Here we see that there's a flip-flop of the region 1 and region 2 recruitments. So what we're seeing is that with movement, we see more recruits in area 2, but then they're moving into area 1, whereas with no movement, we end up with more of the recruits starting off in area 1. We really don't get any information on movement of the adult fish. And so, our movements between areas 1 and 2 is from the tagging of those small fish. And what we see in the differences in long line length composition between areas, and there are some notable differences in the length composition between the areas, that then is going to influence the movement rates. And so, I'm not going to try to interpret all the details here, but we do see that we end up with very low movement rates to and from areas 3 and 4, just because there's really not enough information to decipher that. We profiled on the movement from area 1 to area 2. It's a little spiky here, but I think we get an overall pattern that, it's not that sensitive to it, even though we ended up with a, low movement rates in this area. We're somewhat consistently performing better, but the change in likelihood is not great across these models, not as great as we saw in the overall R0 profiles. And it's the tag composition data that does show, the most consistent changes here in tag composition in yellow, and it's showing, showing that there is a U shape in the likelihood for movement from area 1 to area 2. But the overall result doesn't much change, because again, we saw the model can adjust the recruitment distributions to compensate. So by fixing the movement rate at one level, the model can compensate with the recruitment distribution to achieve essentially the same results. Looking at the four-area model with and without movement, we see it's sensitive to that, which again is not surprising given the differences in removals across the 4 areas. And so, having some areas with no movement and a lot of catch, really forces the model to estimate them well, and the other models, other areas just go along with that. Don't need that. Did a little bit of retrospective. Even though we saw quite a bit of pattern in the recruitment deviations near the end of the time series, when we saw that, I was expecting to see more of a retrospective pattern as we peeled back data, but we don't see very much. And so, it's pretty stable here at the end of the time series. We were able to set up the model with both quarter as year and season within year structures. But the concept of aging is different between the two, and we ended up seeing some differences in the results. We can estimate a seasonal effect on movement, but it's harder with the season within year structure. Here we have, again, our selectivity curves on the right-hand side, our growth curve in the upper left quadrant, and our recruit devs in the lower left-hand corner. And as we go from the year within season model to the quarters, we see different levels of selectivity showing up. And I think this is because as we move to the structure that had seasons within years, in order to achieve enough flexibility in selectivity, we switched to doing it at dome-shaped selectivity in length. I believe this is where we made that switch, and we ended up with a very different flexibility to have dome-shaped selectivity. So it's very hard to have that sort of a dome when we do the season within year approach. So actually doing it as a straight quarters, so we ended up with more flexibility in the age-specific selectivity when we did that. So in that case, I would say that that was a preferable approach for how we approach this. And this is another look at the recruitment, the movement parameters. And got this one in the slide deck twice. So in summary, we see that the 4-area model and the single area model are generally consistent in estimating the scaling parameter when the tag data aren't used. So the tag data certainly are influencing the overall scaling because they're influencing the overall mortality rate. So the tag data are influential. So setting it up appropriately gives us the right regional structure, but we really didn't have enough tag recapture pairs across all the areas to do this as well as we would have been able to with a fuller data set. And because of that, the movement rates are pretty confounded with the regional recruitment, and I don't see a way around that given this quantity of data. So I think that forces us into making some assumptions, using some auxiliary information in order to constrain models like this with that in that regard. There just is not going to inherently be enough information to do that without having a really full set of tag data or something else. So that's what we have. Again, I don't think we've spent as much time on this as we all wanted to, but we feel as though we've got a better understanding of where we stand now. I think we certainly can do some more with the weighting of the length composition data in order to get it to perform as well as we should be able to. Clear that we have underestimated the importance of the Persane length computation data in the way we've set up things so far. But overall, I'd like to open it up to Dan and Max and others who may be on to fill in some of my gaps in our presentation, which I did the best I could, but I think we have a ways to go in order to get a fuller story out of this. So I'll stop sharing there, but let me know if you want me to pull it back up for any slides.
All right, thanks very much, Rick, for your presentation. That was excellent. You did ask Dan and Max and others if they had anything to add, so I'll go to you guys first to see if there's anything that you wanted to chime in, and then I see we have a question in the chat already, but others feel free to raise hands in the meantime.
I see John has a question in the chat. Okay, yeah, and I'm not hearing anything from others, so it sounds like you were spot on there, Rick. So yeah, let's go ahead and if you got it up there, you can go ahead and read it and go for it. Yeah, so John asked, he says that the spiky behavior of at least one of the long line data sets seemed to be replicated in the fit, and I did notice that as well. So given that the selectivity was smoothly asymptotic, I'm wondering how this was done. Well, it may be that the data are following a growth curve, and we have the same growth curve, so the fish are at the right length, and we may well be picking up the modal ages, and perhaps it's just that the spread in size at age was not sufficient to blur that out. So we're able to pick up the spikes where they actually occurred. I'll take a quick look at the sigma R on movement yeah, it was 0.1, so it's not that small. Okay, John says, thanks for your response, Rick. And then we've got, I believe, Dan, your hand was up first. Yeah, go ahead.
Yeah, just a quick comment on the difference in terms of the scaling parameter between the spatial and non-spatial model. I think the Nicholas, the multi-MFCL team, they also highlight this, and I think they basically mentioned about this buffering effect, whereas some area you can serve as a buffer for a lot of biomass that you can get higher biomass, whereas non-spatial model you tend to have lower biomass. I was wondering whether that, with a spatial model where you kind of partitions a model into different region where there's a constraint of, each region has to support certain amount of catch, that tends to act as constraints to influence the scaling parameter as well. So one of the things is that if the model tends to have a higher, for the region model, if it tends to estimate a higher movement rates or higher mixing between the area, then that sort of kind of mitigate that kind of effect. That kind of can probably make the scaling parameter estimate more consistent with a single area model.
Yeah, yeah. In our model, compared to multifan, we did not allow movement from areas 3 and 4 back into areas 1 and 2. Maybe we did have area movement from 4 back to 1, but not from 3. And so I think that might have reduced the flexibility to do the buffering from the lightly fished areas back into areas 1 and 2. Mark has his hand up.
Yeah, hi Rick, thanks for the presentation. Couple of questions, or one's a comment, one's a question. So with the shared catchability in the multi-area model, did you weight those by the area of each of those regions, so that when you share the queue, it's the right thing? Because you can't just share a queue with a right. CPUE standardization. You have to somehow weight it by the areas.
That's correct. That's correct. I would have to defer to that or look at the model files to see how we handled it. I recognize that we do have that capability in SS3 to basically build the area effect into the queue so that you are comparing abundance by area, not density by area. And maybe Dan can respond on that.
Yes, I see Simon raised his hands up because at the beginning of the workshop, we did query with the organizer that, the CPUE standardization we understand is done in a way so that, they have this regional scaling thing built in. So the different scale in the CPUE does reflect, they sort of have done the analysis so that reflects the distribution of biomass among the region. We know it's additional constraint that we kind of additional information that's been put into to this exercise, but in real practice, in a real assessment, probably it's better to just when you have a regional model to just use the catch and CPUE in each region itself to determine its relative biomass distribution. But we find that from my experience, it's really a lot of time it just doesn't work. The model just can't handle determine the biomass distribution among the region. So that additional constraint does helps a lot. Thanks.
Very good.
Yeah, and it looks like Simon has confirmed that in the chat. And Mark, you had something else?
Yeah, the other comment I wanted to make was about the one area model, but it was the areas as fisheries model. And so it looked as though you were using 4 indices, one for each area in the single area model, which is probably a big no-no because they all have different trends.
Don't think we did that.
And it looked as like in the slide on the areas as fleets model, because you had 4 indices. So I'm assuming it was 4 online indices, one for each area.
Oh yes, that would be correct then, but that's what areas as fleets is. So we're not saying that it's the right way to do this. I was just showing that if you did areas as fleets, that's what it would be.
Yeah, because in the one Heikland did, he'd add the areas as fleets for the fisheries, but for the index, it was just a single index across the whole Indian Ocean. Yeah.
Yeah, Rick, I'll ask a question, and I guess I was wondering, and Nicola brought this up about the rec divs early in the period or early in the time series, and the constraint that Multifan had not to use the kind of early period specification like SS had, and you mentioned that too. So I was just wondering if any of the tools in SS, well, I guess they're probably in R for SS anyways, that kind of help guide you to specify that early period, if any of those came out to help in your explorations.
Yeah, I don't think we used the early period. I think we did it all. I'm looking right now. We did not use an early period. So I think, we either had, no divs early on, or in one case, extended the divs back to the beginning. We didn't use the early period divs. That's a separate vector of divs. I do think we have more to learn about the difference between modeling with divs as with a sum to zero constraint versus just treating them as divs. I think we have just gotten ourselves locked into doing it as sum to zero because that was the common way to do it for so long. And we are just defaulting to that without critically looking at its impact, especially when we have such heterogeneous information about rec divs over time. So I think, there are various options in that regard to be explored. We just need sort of a definitive paper to be done comparing those options. And I think that's important as we start developing new assessment models, that we get a better handle on the relative importance of that sum to zero constraint and what are the constraints it imposes on us. So how a model treats those early divs would be part of it.
Yeah, thank you, Rick. And just for everybody, we're kind of into the period of open discussion on anything that was presented today, or ideas of any sort. So feel free to ask questions to Rick, to the group, to Nicola. Dan Gaethel, go ahead.
Yep. Yeah, I just want to say those are two great presentations. It's a lot of stuff to kind of digest there. But it seemed like one of the main issues that both presentations were really harping on was this issue of the tagging data and what is sufficient tagging data for a spatial model. It seemed like both groups kind of approached it like it was pretty much necessary to include the tagging data in order to estimate movement. But then once you start analyzing the data that's in there, it's short time series, really localized in terms of the temporal and spatial distribution of the tag releases. So I wonder if anyone could kind of elaborate on, what they feel like would be, in theory, sufficient tagging data, and also whether marker capture data is even what we would define as sufficient at this point.
Yeah.
So yeah.
Yeah, I'll make a quick stab at that. I think it is important to have the tagging data in a model like this, but I think the question is more, why did we do a 4-area model when we knew that we didn't have tag data to really help set up a 4-area model? Why didn't we start with a 3 or a 2-area model, given the information that we had? And I think it's a case of, in a real assessment, you'd have a little bit more anecdotal information, the history of the fishery to help in your model configuration. But here it would be harder.
Yeah, go ahead, Simon.
Yeah, I guess just to the history of this project, the reason that we went with the 4-area model is that's the approach that they use in the Indian Ocean stock assessment. So in a sense, this really is a real model, but in this case, the data that you're fitting to are they're generated from an operating model that's internally consistent. And so if you're when you get those conflicts in the likelihoods and so on, that's a result of probably some conflict within the model setup itself, the model that you've developed, rather than, yeah, and just the difficulty of fitting those different kinds of data with a simplified spatial model and with the lack of information that you have about things like movement rates and so on.
Yeah. I think some of the same questions come up in the original model, frankly.
Yeah, definitely. It's a very good question why it's done as a 4-area model, and it's probably not a good idea to do that.
Yeah, go ahead, Mark.
Yeah, I've got another question, but to follow up on Simon's one, just a clarification of how the operating model works. If the operating model is on a finer spatial scale, that's my understanding, but it has 4 areas, does that mean the movement rates on the small spatial scale are different in those 4 areas, or am I confusing things?
Yeah, the operating model is actually not 4 areas, it's 221 areas. So yeah. You've got, yeah, the fish are actually moving around within those 221 areas according to the sea surface temperature, like they're following patterns in the SST and they're following the chlorophyll distributions. And that's kind of how we drive the fish around. And then, of course, we generate data and we put it into those 4 area structures. And then you have to fit models to that, which is a replication of what we all try to do when we fit stock assessments. And I guess I might explain a little bit more about the sample size weighting as well.
Well, before you do that, just to clarify, the 4 areas that you've chose, it sounds as though they have nothing to do with the actual movement or the population structure. Or how were those 4 areas chosen compared to the biology of the simulated stock?
That's probably a historical question for the Indian Ocean Tuna Commission, because that's why they're set up that way. That's the way the regions are set up in the yellowfin assessment for the IOTC. So we just basically this whole simulation is based pretty closely on the IOTC yellowfin data set and the way they've set up their stock assessment.
But the movement is independent of that, and it may or may not be relevant to those 4 areas, depending on whether sea surface temperature that's driving movement is related to how the Indian Ocean originally set up their areas. Is that correct?
The movement estimates come from fitting the SPM operating model to the data set. So those, like all of the data were put into the SPM model, and then those movement rates were estimated, and then that operating model was used to generate a bunch of new data sets.
But the movements aren't referenced, as Mark was saying, to these 4 areas. So there's an inherent structural mismatch going on.
Yep, which is pretty realistic.
Yeah.
Looks like Dan Fu, you might have more to add to this conversation here.
Slightly different but related. I was just wondering, related to the discussion of utility of the adequacy of tagging data in those type of model. Including the tagging data, there's 2 functions really to use it. One is to estimate movement, the other is abundance. I believe in SS3 and multi-MFCL, when you're building a spatial model, you have to estimate if the tagging is distributed across the area. You have to estimate both movement abundance and fish mortality at the same time. No, you can't. I mean, the reason I'm asking it because to estimate, using tagging data, estimate abundance and movement, they're based on slightly different assumption. There's different assumption that needs to be made. I mean, for fish mortality estimate, abundance estimate, the tags has to be homogeneous mixing. But to estimate movement, I guess, it's better to use archive tags, but conventional tags, I guess it's a question of how representative those recovery represents movement. So I was wondering whether there's a need to allow, those software to, I mean, if you believe one of the assumptions is not made, whether that kind of can be turned off to allow the model just to estimate either abundance or movement or the other way, if that's a sensible thing to do. Because we have a lot of discussion now. Yeah, my point really is different assumptions that needs to be made on the different part of the tagging.
I saw Mark's hand and then John's hand. If you had a response to Dan's question.
Yeah, I don't have the response to Dan's
I have
question.
a response.
Okay, yeah, go ahead then, Rick.
Just quickly, Dan, you can weight the two components separately. You have different lambdas.
Okay, we'll go to you, Mark.
Well, in response to Dan's question, there is the catch conditioned tagging likelihoods that Rick McGarvey has for just estimating movement and not things, but I don't think that's implemented in the software at the moment. The thing I wanted to point out was that there's a couple of big issues with the tagging data, and one of them is tag mixing. And the problem of tag mixing is you've got to choose a tagging, a period to try and remove those tags that haven't mixed yet, so you don't get a biased influence both on movement and abundance. But I guess abundance and fishing mortality might be more important. The thing that we're doing in the EPO now is we've got Tobias and Anders working on this fine scale spatial model, which can model the tagging data to estimate abundance when you don't have to worry about the mixing, because it takes that into consideration because it's done on a fine scale. And then that can be used as an index of abundance or of absolute abundance that you put back into the stock assessment model. I'm not sure when they're going to be in a stage where they can actually apply that to the simulated data, but I think at some stage it might be a good idea to apply that method to see, if that's going to be more reliable than putting it directly into a 4-area model.
Yeah, I think that's a good idea. It's a simulation experiment 2.0. Let's see, John, you have your hand raised.
Yeah, thanks, Aaron. Just on this spatial mismatch thing, yeah, it'd be kind of interesting at the end of this process to see how much better we could do if we had some flexibility to better match the 4-region specification, if we were doing this based on, things like the environmental data and some information about how that was likely to impact the distribution and movements, etc. And I guess at the end of the day, I mean, these models are to be used to provide useful information for fisheries management. So it would be interesting to see, how much do we actually suffer by through these mismatches. Certainly we suffer in terms of biological reasonableism, but at the end of the day, do we suffer that much in terms of the quality of management advice and how much those indicators may or may not be robust to those sorts of misspecifications. So just, if we're going to take this forward in the future, those might be some interesting concepts to explore further.
I'll just follow that one up. I think that's a really good idea. The data actually are available. All of the 221 cell data are available. So I guess the thing is to decide on the configuration that you want to try, and they can be, the 221 cell data can be manipulated into whatever structure you like, really.
Yeah, and I'll just add on to that I think, of course, everybody has limited time to continue to explore things, but if time is available, though, those, as Simon says, there are other alternative data that are already simulated that could be imputed relatively quickly into your already existing workflows. If that's something that was of interest and time allowed, that would be very interesting to present at the workshop, or at least discuss some comparisons. That would be fantastic if somebody or a group or several groups wanted to try that. I did see a hand. Sorry, I'm clicking back and forth. Craig, I see your hand is up.
I think Mark might have been a bit before me. If you want to go, Mark.
I'll let Craig go. I've been talking enough, so I'll wait for after him.
No, mine. I just had quite a specific question actually, because about the catch as errors, or the catch condition in the first presentation. I'm currently going through that well, I've got a model that estimates 3 Fs and trying to move it towards a spatial model as well, towards a model that will solve for those Fs. But there was a part of me that was a little bit reluctant given the computational overhead, and I just wanted to have a general query if anybody had any insight on whether, although they're free parameters, really, because the CVs are so small on our observed catch, they're really pinned or constrained. And I just wanted to know if anybody had any insight on, whether it's definitely worth doing, or it's not, just keep the free Fs. But maybe that was too generic for Nicholas or Rick. I imagine you've kind of gone through that with stock SS as well.
Yeah, go ahead, Rick.
Yeah, we've not looked at constrained Fs. We've treated Fs as free parameters nearly entirely. The only place where we start seeing that break down is when we are fitting to both discarded catch and retained catch. And now the same F needs to contribute to both. And that is, raised some questions about, just how to go about dealing the balance between the basically the precision on the retained catch, which is generally very high, and precision on discarded catch, which generally is low. But nevertheless, they are going to be somewhat at conflict if they're both influencing the same F. That's the only place we're starting to look at that.
I saw some other hands pop up. If others wanted to also respond to Craig, just jump right in.
Yeah, I had a quick response. I mean, in MFCL land, I think we started off the other way compared to stock synthesis, and that we were routinely using this sort of catch errors version, which, you can think of as being the sort of fairly constrained computation of fishing mortality using making extensive use of fishing effort information in those computations, along with estimates of catchability and what we call effort deviations. Now, the upside of that is that you don't have to do like an internal Newton-Raphson to compute the fishing mortality for each catch observation. But the downside is that even though the effort deviation parameters are constrained by distributions, etc., they are formal parameters in the function minimizer, and so that attracts an overhead as well. You've got to compute gradients, etc., at every function evaluation. So, it swings and roundabouts to some extent. I think in terms of computational efficiency, there's, where we've done those sorts of direct comparisons, there probably isn't a lot in it between catch conditioned or the catch errors type approach. But obviously it's going to be a little bit case specific, depending on the number of fisheries that you have, etc., number of observations.
Nicola, did you want to jump in too? Or did you have a new question?
It's a comment to the same question that Craig had, but I think John mostly covered it.
All right, we're kind of winding down here. Mark, you've had your hand up and being patient. I'm going to give you the last question. Go ahead.
Okay. Yeah, it's more a comment about the mismatch between the fine scale and the large scale spatial areas. And so in Haikun's analysis, he actually estimated what the areas were in this fishery as areas approach, which presumably was somehow approximating the areas, which might be different than those 4 areas. So it might be a good idea for people to go back and look at that to see how close those areas that Haikun used were to the current areas, and possibly run one of these spatial models with Haikun's areas rather than the original areas, or do the same approach but maybe do it on CPUE or something else that may be more related to the actual spatial fishery structure rather than just the link frequency structure.
Thanks, Mark. Tying in webinar 1 with webinar 2, you've been to these types of rodeo before, haven't you? That was a great ending comment. I'd like to thank everybody for coming, but especially the presenters, Rick and Nicola. Really great presentations today. Thanks for those. Also the Multifan team and the SS-IOTC team for being here today. And of course, everybody that's online that's been listening and participating, we thank you as well. And I did just want to close by letting everybody know that the next webinar that we have is on December 12th. I have listed here Pacific time. Sorry, I don't have all of the time zones converted here, but we'll be hearing from another team from the ICES region with SS, as well as a team from Gadget, and then also a team from Castle 2 that's going to actually be looking at different species, the other data set that we had simulated, Antarctic toothfish, so that'll be quite interesting as well. So we really look forward to seeing everybody in a little less than a month's time. And again, thanks everybody for coming and staying up late or whatever time zone you're in. We really appreciate it, and hope to see you at the December 12th webinar 3. Thanks everybody.
Good night.
See you. Bye-bye.
Thanks, everyone.